Hello, everyone. This is the lecture for section 2.2, 2.3, and 2.5 of our Math 210S course, the limit of a function and limit laws. Okay, so as I've mentioned probably in class, right, this is the first bona fide section that deals directly with calculus, okay? Up to now, we've been covering everything that we need in order to describe certain things, right? And I gave you guys examples, made you describe some stuff, right? But now we're going to get into some much more difficult things, much more complex, much more, how do I say this? Much more uh, abstract thoughts, okay? And that is what the limit deals with, okay? So the best way for me to, what we'll start to do first, right, is we're going to do an intuitive definition of a limit, and then we'll move into more robust and rigorous definition of the limit itself, okay? Okay. So the best way for me to just sort of show off what a limit is, right, is let's consider this function right here. So I'm going to be messing with this function in particular right here, okay? All right. First thing I'm going to do is I'm going to find the domain. So hopefully you guys remember, right, from the first couple weeks of class, that the domain is basically all the possible x values that I can plug in that give me a valid value. In this case, right, the two things that we can't do, right, is divide by 0 and take the square root of a negative, right? Those are the two things we can't do. In this case, it looks like we might be dividing by 0. And the division by 0 happens when x is equal to 4. So we can't have x is equal to 4, right? So then our domain for this, right, is going to be negative infinity to 4 union 4 to infinity. Okay, notice that my interval, right, notice that my domain is skipping over the value 4. Okay, now what I want to do is I'm going to use a graphing utility to sort of show this off, right? But what I'm going to be doing is we are going to try to start looking at values that are getting closer and closer to 4. Okay, and for me to do this, okay, I am going to do a split screen. I'm going to put our notes on the left, and I'm going to grab Desmos and put that on the right. There we go. Okay, so I'm going to turn on this function right here, the one that we're concerned with right now. There it is. That is the graph. Notice how it looks very much like a line, right? Okay. I'm going to move this over a little bit. And actually, I'm going to zoom out so I can, there we go. Aha. Okay. Like I said, I want to start getting closer to this value right here. I want to get closer to 4. Okay. Notice that 4 is the number we can't plug in. Okay. And I'm trying to get closer to it. Okay. So we can't plug it in. So I'm going to put an X there for now to tell me that I can't plug it in. Okay. But I want to get values closer and closer. So I'm going to do this. I'm going to do 3.5, 3.6, 3.7, 3.8, 3.9. Notice that my X values are getting closer and closer and closer to 4. Okay? All right. And what I'm going to do now is I'm going to go ahead and add in here a table. Okay? I'm going to go ahead and get rid of this and make it X. And since I called it f of x, I'm going to change that to f of x. Now I can put in some values for me to have this thing compute, right? So 3.5, 5, 3.6, 3.7, 3.8, 3.9. Okay, now I'm just going to go ahead and copy those over. So I want everybody to see what's happening, right? At 3.5, my f of x value, my y values are is 7.5, right? The next one is 7.6, 7.7, 7.8, 7.9. Okay? Okay, let's save that there for now. And I'm going to move over. I'm going to do the same thing from the opposite side, but I'm going to come down to it, right? So it's going to be 4.5, 4.4, 4.3, 4.2, 4.1. Okay, and I'm going to do the same thing. I'm going to get rid of these x values. Okay, I'm going to start from, so I'm going to do 4.1, 4.2, 2, 4.3, 4.4, 4.5. I'm going to just copy those over. Okay, and we get 8.5, 8.4, 8.3, 8.2, and 8.1. Got it? Okay. That's all I needed Desmos for. I'm going to move this out of the way so we can look at our table entirely. Okay, I'm going to zoom in so we can, there we go, there we go. Okay. So, I want everybody to notice something, right? Remember, I just said right here, we just determined, right? The domain for this function is everything except 4. We should not be able to plug in 4. And that's still the case, right? But look at what happens, right? This way. As I get closer this way, okay, on my x values, the y values are getting closer and closer to something else, right? And then same thing from this direction. If I start heading toward x equal 4 in this direction, right, my y values are getting closer to something else, right? And they just so happen to be the same thing, right? So if you take a look at this, right, it looks like my x values, or sorry, my f of x values are approaching the value 8. You guys see that? So from the bottom, it's going 7.5, 7.6, 7.7, 7.8, 7.9. And then from the top, they're dropping, right? 8.5, 8.4, 8.3, 8.2, 8.1, all the way to 8. Makes sense? So what we did just now, let me actually go back to the table, and I hope that, there we go. If you take a look at the dots, here we go. Hopefully you guys see that there's a set of dots here. That, 2, 3, 2, 1, right? Those dots are leading us somewhere, right? This is still undefined at 4, right? But you can tell there's a clear direction. Yeah? Okay. So what we're saying here, right? What we're saying here is what's happening as our x values get closer to 4, right? Right? We're saying our f of x values, right? Are approaching, right, y equal 8. We are saying here, right, that as our x values approach a specific value 4, our y values are approaching a specific value 8, even though 4 cannot be plugged into our function. Okay? All right, we're getting somewhere. Let me do one more example, and this one's going to be a little wilder. This is something that, this is a function that people don't, regularly think of, okay? Consider this function right here, okay? I know I haven't covered that value e yet, right? But we will once we get to exponentials, right? Once we get to exponents. But for now, let's just go ahead and treat e as a number. Desmos, thankfully, knows what e is, okay? But thankfully, we don't need the value e just yet. What I do want to concentrate on right now is the domain, right? So again, the domain is all possible values that we can plug in, okay? Okay. we have a division there, that 1 over x, that's an exponent to the e, okay? That value can't be 0 on the bottom, right? So we have to skip 0. So according to this, right, x cannot be 0. So my domain should be negative infinity to 0, union 0 to infinity. I have to skip over it. Okay? And as I did before, I want to approach 0 from the left and from the right. So I'm going to make this my 0. Okay? And I'm going to start negative 0.5, negative 0.4, negative 0.3, negative 0.3, negative 0.2, negative 0.1, and then it's 0, right? And then I'm going to do the same thing from up above. 0.5, 0.4, 0.3, 0.2, 0.1. So look at what's happening, right? From the positive side, I am approaching 0. From the negative side, I'm approaching 0. And what we're going to do is we're going to look at what's happening to our y values. Again, I'm going to let Desmos do a fair amount of my thinking here. I'm going to turn this one off. Okay, I'm going to erase the x values from the previous table. Okay, and I'm going to go g of x. I'm going to turn the new one on. Okay, and for this one, I got to zoom out a little bit and I got to arrange a little bit. So stay tuned a little bit. There we go, and there we go. Woo! All right, there it is. I'm going to change this to g. Okay, so that it can compute values for me. I'm going to do this again. I'm going to start plugging in different x values, and it's going to compute the y values for me. Okay. Negative 0.5, negative 0.4, negative 0.3, negative 0.2, yep, and 0.1. Okay, so this is going to have a little bit of rounding in it, but that's okay. 0.88, what, 8807, right? 0.9241, 0.9655, 0.9933, and then the last one, 0.9999. Okay, awesome. I'm going to go ahead and scooch this over, right? Okay, I'm going to delete these x values so I can do it from the top end. So let me delete. Okay. 0.5, 0.4, 0.3, 0.2, and 0.1. Okay. And I'm going to scrunch this open a little bit. There we go. Okay. 0.5, I got 0.119. 0.4, 0.075, 0.0344, 0.0066, and then this one is going to be, this is going to be 0.00045. Yep. Yep. Okay. Let's put those tables front and center again. Here we go. Okay. So, gonna do it again, right? We're gonna get closer to 0 from the negative end, and then we're gonna get closer to 0 from the positive end. Notice what happens this time, right? We know we can't plug in 0, right? But in this case, if we approach it from the negative side, right, we get closer and closer to a specific value. In this case, it's 1, right? But the other end, we get closer and closer to 0, right? So what can we say happens to our f of x when x gets closer to 0? We have no idea. In this case, for now, right? Right? Different values. Okay? If we approach from the positive side, that's getting closer to 0. And if we approach it from the negative side, that's getting closer to 1. It's approaching two different values. So what do we do? Okay? This, in and of itself, both of these examples, I believe, pretty much encapsulate the reason why we have this idea of a limit. Okay? So the first thing I want to cover is the definition itself of a limit. Okay? We write this out. Okay? If f is a function and the values of f of x get arbitrarily close to a number L as x gets sufficiently close to x equal a, then we say that the limit of f of x as x approaches a is equal to that value L. And we denote it this way right here, just how I have it highlighted right there. Okay, so essentially what we're doing is, let me go ahead and draw, right? And let's say this is our function, right? Whoa, I can't make it do a sharp turn like that, but there we go. There we go. F of x, right? Suppose that's our f of x, right? And right here, this is our a. So then that means this value right here, right, is going to be a value L. Now, look at what I'm doing, right? This is a value L, not f of a, okay? A value L. Because as we saw from above, right, right here at this point, this value may not exist, right? But we can still reference the point that it's approaching. So what we basically say is this, that if we come at it from, the positive side, right? Think of this like, think of it as breadcrumbs, right? Where are the breadcrumbs heading toward, right? If you take a look at it from the positive side, and if you take a look at it from the negative side, right? It's heading to a value L. This is the L, right, that we're speaking of here. Okay? So, let's go back to our two examples. Okay? For the first one, we would say, okay, and I'm going to actually write it. Let me do, I'm running out of colors. Let me go ahead and grab this one. No, let's just keep it pink, and I'll highlight it. We would say that the limit as x approaches 4 of my function f of x is equal to 8. And I'll highlight it in pink. Okay? X equal 4 is not a value we can plug in, but we can follow the breadcrumbs. We can follow the ant trail, right? And we can see that all the y values start heading toward y equal 8. Okay? Okay, let's move on to this other example, right? In this case, we saw that it was approaching two different values, correct? So we could make a determination about, something that we can say for the, whoa. Oh no! There we go. Hopefully I didn't move it too much. Okay, there we go. We couldn't make a determination, right? The breadcrumbs were leading us to two different locations, right? Make sense? So in this case, we couldn't say that it was approaching one specific value, right? Whenever that happens, we want to find the limit as x approaches 0 in this case, right? Of my function f of x, and that does not exist. Okay? if we can't nail down one specific value where our y values are headed toward, then the best we can say is that it does not exist. That is it. This is the idea behind the limit. Okay? So, what I have after this is some quick checks. Again, I'm going to have you guys do these during our class, during our quick check time. Okay? Okay. We're getting there. We're getting there. Now that we know an intuitive definition of a limit, I need to specify a little bit more stuff. I need to refine our definition, at least the conceptual one that we have for right now. I want to refine it a little bit so that things a little later, right, make sense. A lot of it is just to keep our thoughts straight, really. Okay. Okay. So we use this definition in pre-calc. Okay. And the reason why is because it shows up in calculus. Okay. So notice, I want everybody, I'm going to do my space pen. Whoa, too big a space pen. Let me tone it down. You see that right there? I'm going to keep circling it. Okay. Remember when we did x little arrow a negative, right? We had already defined that. We defined that as us approaching x equal a from the negative side, right? Now we're going to combine it with the rest of calculus. Now we're saying what happens to our y values, right? That's what this is saying. What's happening to our y values as I'm approaching x equal a from the negative side? If it approaches a specific value, right, then we say the value is L, that the limit is L, right? And then same thing if we do it for the positive. Okay? Okay. So a theorem that's in our textbook, okay, the limit of a function, okay, and I'm going to go ahead and define this. When we say the positive or the negative end, or the positive or the negative limit, right, what we are calling those are one-sided limits, okay? Okay, now to our theorem. The limit of a function, okay, the one that I was writing up above, right, the limit of a function, notice that it doesn't have the plus or the minus as an exponent. It exists if and only if both the left and the right hand limits exist. Okay, so that means both of these, this one and this one, have to exist, right? And they have to be equal to the same value. Okay, all together, right? If you have the limit as x approaches a from the positive of an f of x, if that is equal to the limit as x approaches a from the negative end, right, of f of x, then that's got to be equal to the limit as x approaches a, notice I'm not writing a little exponent here, of f of x. Okay? So essentially saying, right, this one exists, right, if and only if both of these exist and are equal. Okay? So what does this look like? An example. Okay. So let's go ahead and do, these are supposed to be done in columns, so I'm going to do this column first. Okay. I want to approach, for this first one, for all of these, I want to approach -3 from different directions and then make some conclusions, right? Okay. The first one, I am approaching -3 from the positive side. So I'm doing this. La-di-da-di-da, tum-ti-dum-ti-dum, right? I'm getting closer and closer to -3 on the x-axis, so this value on the x-axis, from the positive side, right? And if you notice, it is getting closer and closer to, I'm going to say it's 3. I'm going to round. So my y values are getting closer to 3. Got it? Okay. I'm going to do the exact same thing from the negative side. That's what this one's asking for. Okay? So la-di-da-di-da, tum-ti-dum-ti-dum. This one, it looks like it's getting closer to -4. Oh, the 3 got erased, -4. Okay? Okay, now I'm going to do what I like to call the flat limit, the one that doesn't have the positive or the negative on it. Okay? Since these two, since those two are not equal, no ifs, ands, or buts about it, this one does not exist. Okay? We are looking at the breadcrumbs. We are looking at the ant trail, right? If they don't go to a very specific point, one specific point, it does not exist. Okay? It just so happens that if you look at the function value for g of x at -3, this one also does not exist. Got it? Okay, next one. Let me get rid of my little dots of stuff everywhere. There we go. Come on. Can I erase bigger? Yes, I can. Yay. Whoa. All right. I guess. There we go. Let me do that one again. Okay. Next set. Now I'm approaching +2. Okay. So I'm approaching this value. Okay. So hopefully you guys see what's happening. When I approach +2 from the positive side, so la-di-da-di-da, tum-ti-dum-ti-dum, right? My y values are getting closer to 1. Doing the same thing from the other end, I'm getting closer and closer to 1 as well. Since both of these are equal, right, the flat limit has also got to be equal. So we can see, right, that my y values coming from the positive and the negative side, they are approaching one single solitary value. That value is 1. Okay? It just so happens, right? You guys see this open circle, right? We know what that means. It means that our value, our function is not defined there. So, means in this case, right, g of 2 does not exist. So our function at this point in particular does not exist. Okay? So take this as an example where a function does not exist, but it can approach a value, much like example 1 that we just covered. Okay? Last set. Yep, yep. Okay. In this case, I want to approach our value x equals 0. So I'm approaching this right here. Okay? So I'm approaching this x value. I'm going to actually fill it in hot pink. There it is. Okay? From the positive end, we can see that that is 2. From the negative end, that is also 2. So since these two are equal, the flat limit, and that's not supposed to be there, so that's my bad, that's supposed to also be 2. And it just so happens this function is defined at 0, so this is 2. So usually, if your x value is, or if your f of x values are defined, right, then it's going to be the function value at that point. Okay, if it's not, then you have to do the limit thing. Okay? Okay, let's move on. So now that we have this idea of a limit sort of worked out, at least conceptually, heavily conceptually right now, yet really, really rigorous. Believe me, what I'm covering right now is fairly rigorous a description for the actual definition of a limit. Okay? We say, let me do this definition right here. We say that this, right, that the limit as x approaches a, either from the positive or from the negative of f of x, is equal to infinite. It's equal to an infinity. Okay, if the values increase without bound, same thing, equal to negative infinity if the values decrease without bound. Okay, and it's got to be equal to this if both go to the same infinity. So if both the positive limit and the negative limit go to infinity, then it's also going to be equal to the flat limit, this one. Okay? Okay. So I got to put up this note. By the limit definition, okay, we are looking for, by the limit definition, infinite limits do not exist, okay? Because the limit was supposed to be defined as the approaching toward a specific y value, right? Infinity is not a value, okay? But they are used to describe a function's behavior still, okay? Okay, finally, we get to this example right here, this definition right here. This is the bona fide example now of a vertical asymptote, okay? A vertical asymptote, okay, is wherever you have an infinite limit. So basically, where any one of these three are true. 1, 2, 3. Okay? All right. Let's show this off, huh? Suppose we have this function right here. We know sort of, kind of, that the graph of this does this, right? So there's going to be a vertical asymptote at positive 3. And there's going to be a horizontal asymptote at positive 2. Okay? The graph of this looks something like this. Whoosh down that way, and then this other one goes like this. Whoosh down that way. Okay? Okay. Throw this into Desmos, you'll get something pretty close to that. Okay? I'm not expecting exactness. That's why I'm letting you guys use Desmos on it. Okay? Now, what I do want to cover is this. That. Okay? Remember that at 3, we have a problem. There is an asymptote there because we can't plug in 3, right? But we can look at the limits for them. So for the limit approaching 3 from the positive end, right, we are looking at this thing right here, that arrow. You guys can see that it is growing without bound, right? Come on. Stroke eraser. There we go. Infinite. Okay? Since it is growing without bound, that is infinite. If you take a look at the other end, that one, right, that is decreasing without bound, right? So then that is negative infinity. Okay? Same rules apply, right? Since both of these limits, right, they don't match. They're not heading toward the same direction, right? So then what we can say here is the flat limit, the one without the positive or negative there, right? The flat limit does not exist. Okay. So we have a general idea of what a limit is supposed to work like, okay? Let's move on to limit laws. So from the definition of limits, okay, from the definition of limits, we get these limit laws. Okay, basically, if you were to prove them out, right, they are going to hold true for any limit that you can possibly think of. Okay, so let me cover them really quick. Suppose you have f of x and g of x, right? And suppose that the limit that approaches a specific value a is equal to L for f, right? And then the same thing, g approaches a value m, okay? And L, m, and c, so c is going to be another value that we're going to play around with right now, are real numbers, okay? Then we have the following things that are true, okay? The first one, the limit of a constant number is the constant number itself. Okay, that one's simple enough. Okay. The limit as x approaches a of f of x is equal to f of a if x equal a is in the domain of f. So if there's no problem with me just plugging in a to my function f, then I can do so. That's what this one says. Okay. Okay. If I have the limit as x approaches a of the sum of two things, right, then I can break them up into their parts. And it's going to be equal to the limit of L plus or minus the limit of M. Got it? Okay, next one. If you have a constant times a function, right, you can pop out the constant and then do the limit as x approaches a of f of x. And that is equal to the product, the multiplication of c and that value L. Okay? If you have the limit of a product, you can break them up into the product of limits. Okay? And it's going to be the L times the N. Now, I got to preface this one. These have to be true separately. Okay? And there is a problem here when you get into a couple complicated fuzzies that might mess this one up. Okay, so just make sure that both the limits separately exist. Okay. Okay. Next one. If you have the limit of a quotient, if you have the limit of a fraction, it is equivalent to the fraction of the limits, and it's going to be L divided by M, so long as the limit of the g of x, basically the limit of the bottom, is not equal to 0. We still can't divide by 0, even if it is with limits, right? Okay. Next one, suppose you have f of x to the n power, okay? Suppose that you have f of x to the n power. Okay, that is equal to the limit of f of x to the n power, right? And that means I can grab the L and just take it to the n power. That's it. Simple enough, right? And then 8 is an extension of that. Let's say I have the limit of the nth root of f of x, right? That is the nth root of the limit, which means I can take the nth root of L. Got it? Okay. Moving right along. So how do we actually compute these if we don't have a graph, right? Let's say I actually just give you a function. How do we compute these things out, right? Okay, in order to compute these out, right, so long as so long as the x value is in the domain, there's no problem with us just straight out plugging it in. That is actually number 2 in the list that I just covered, okay? So, for example, notice, you guys see that 2. I need to find the limit as x approaches 2 for this one, right? Okay? Is there a problem with me plugging in 2? Like straight away? Nope. I'm not dividing by 0, and it doesn't look like I'm going to be taking the square root of a negative anywhere. So I can just go ahead and throw it into the function, right, and get a value. So it's going to be the square root 2 2 cubed plus 9, and that square root, plus 2 times 2 minus 1, all of that squared. And if you compute this out, you're going to get something along the lines of the square root of 25, right? Plus 9, 14. Bam. Okay. So just to double check, right? Go ahead, graph this. Grab that and throw it into Desmos and look at what happens when it approaches 2. It should be getting to positive 14. It should be getting closer to 14. Okay? Okay. Some quick checks. Practicing just evaluating a limit straight away. Okay? The problem becomes when our x value is not in the domain. Okay? So example, like this one that I have here, okay? I want to find the limit as x approaches 1 of this thing right here. Notice, right, that x squared, let me actually write it out with the value plugged in. 1 squared minus 1 is equal to 0. That produces a bad thing on the bottom, right? We're dividing by, so we can't directly plug it in. So what do? Right? Another sort of problem, right? I have the graph of this on the right-hand side of the screen, right? And we could tell, here's the point. This is our point of concern right here. If you were to graph this, right, and you come real close to this, it'll say undefined. It'll say undefined. But we can see from the graph, it is heading somewhere. And it looks like it's heading to, right, 3 halves, right, or 1.5. It looks like it's heading there. We have no idea, right? But it looks like it's definitely heading somewhere. We just don't know where. Okay? So how do we solve these, right? If we know that our x value that we need to plug in, right, is not in the domain. Okay? And the way that we're going to do that, right, is essentially we are going to eliminate the thing that's on the bottom that gives us our problem. Okay? So one thing I want to show you all is this, right? The first thing I got to show you is this. I think I covered it in a previous example. If I have x cubed minus a cubed, that is equivalent to x minus a, x squared plus a plus ax, sorry, plus a squared. Okay? Why did I show you this? I'm going to factor the top a little bit. This is that thing on the bottom of the screen is one of those things that sometimes you need to pull out of your sleeve every once in a while. X squared plus x plus 1 all over. The bottom factors to this, x, and I shouldn't put a there. Come on. Minus 1, sorry. And then the bottom is going to be x minus 1, x plus 1. Okay? Now, hopefully you guys remember this from our previous sections, right? In our factorization that we just did, we have a plus 1, we have a x minus 1, sorry, on the top, and an x minus 1 on the top, and an x minus 1 on the bottom. They should cancel. If you remember what happened back in a couple sections ago, right? This told us we had a hole somewhere. In particular, we had a hole at x equal 1 in this case, right? Exactly where we're supposed to have 1. Okay, but now, that's not the point here. We need to find this limit as x approaches 1, right? Those two things canceled. The things up front canceled. We get left with this limit as x approaches 1. Give me a second. There we go. As x approaches 1 of x squared plus x plus 1 divided by x plus 1. Okay? Now notice, there is no problem with us plugging in 1. There is no problem with us plugging in the value 1. So what we get to do now is this. 1 squared plus 1 plus 1 all over 1 plus 1. And look at what we get. That's going to be 3 over 2. Exactly where we thought that limit was going to go. Okay? So now, look at this. Okay? We found the limit of something algebraically. That's what this point was, right? Okay? Now, this brings up a very good sort of game plan when finding limits altogether, right? So notice, like I said, the value x equal 1 is not in this domain. Okay? So the game plan here, and this is the case for any one of these limit problems where the value does not work just by plugging it in, right? We need to mathematically eliminate the terms that contain that value that are not in the domain. And we can do that by any means necessary in this case, right? Absent throwing it just completely out. So somehow you need to make it cancel. Somehow you need to make it subtract away. Somehow, mathematically, you may need to make it disappear, just like we did up here, right? The x minus 1 is what was giving us the problem in both of the factors on top and the bottom, right? So we eliminated that somehow in order to properly compute the limit. Okay? Okay. So what comes up after this is quick checks. These are some common ones. I'm giving everybody, for these, I'm giving everybody a little bit of a hint as to sort of the technique that we're going to need to solve these out. Okay? All right. Moving right along. Okay? No matter what, you can grab the functions and plug them into Desmos to visually see. Okay? So try these out. We'll go over them in class. Okay. Next up is a couple of theorems about limits. Okay? The first one, this would seem, it looks complicated to read out, right? The picture makes much more sense. So suppose that your f of x is smaller than your g of x, right? Then the limits should maintain the order. So basically saying this, right? So suppose this right here, right? Suppose this is g of x, right? And suppose this, right, is f of x. And we want to approach this value right here. That's a, right? So we know that we're trying to approach these 2 points right here, right? Okay? This value right here is L, right? And this value right here is M, okay? If G is higher than F, then L's got to be higher than it. That's it. That's all it's saying, right? So this is L and this is M. So the order is maintained in terms of limits. Got it? Okay. Next one. This one's pretty important if you ever do study math at the higher levels. Okay. It's called the squeeze theorem. Okay. And this one requires 3 functions. Suppose you have this ordering for your functions, okay? Suppose that f is the smallest, g is the biggest, and h is something in between, okay? So let me draw it real quick. So here's g of x. This is the big one, right? So this is g of x. There's h of x, so this one. Well, this is g of x, sorry. This is g of x, right? Suppose there's another one that's smack dab in the middle. It can be whatever it wants. It can do this, but that happens, okay? Where all three of them sort of head to this one common point, and we want this limit right here at a, okay? Specifically, suppose that the limit of f and the limit of g is equal to L. So that we're talking about this thing. This. There we go. Okay, got it? Notice that the limit of G, the top one, and of F, the bottom one, the absolute bottom one, and I've mislabeled the bottom one. That's supposed to be F. My bad, my bad, my bad. Okay? The limit of G, the top one, the limit of F, the bottom one, they are both L. Okay? At A. Then it essentially squeezes the limit of h of x in between the two. That means the limit of the middle one must also be L. Okay? So, what does this mean? Okay? I've got, this is actually how you find limits for much more complicated ones at specific points, okay, when you do the higher level math. Okay? So I'm going to use the squeeze theorem. I can't, this is very rudimentary here, just to sort of show you an example of what's going on. Let's say I wanted to find this limit, right? We can tell, I'm going to highlight it in pink here, it is 0, right? Okay? But the way that we're going to do it is this way. This is x squared, right? And this other one, this other green one down here, is minus x squared. So I can say this, that minus x squared is the lower one. Positive x squared is the higher one. And x squared cosine of x is right smack dab in between. Yeah? Two more things need to be written down. Limit as x approaches 0 of positive x squared. Both of these limits are equal to 0. Right? So therefore, it sort of squeezed the middle one, the one that we want, this one right here, right? Sort of squeezed that one smack dab in the middle. So then therefore, right, the limit as x approaches 0 of x squared cosine of x has got to also be 0. Okay? So the last thing I need to cover for this section is the precise definition of a limit. Now, admittedly, this is probably for the large majority of you, unless you're going to be studying math, specifically math, going out and getting a bona fide math degree for the rest of your life. That's all you're going to do. You're going to be the only group of people, right, that are going to see this. Everybody else, if you're going for anything else other than math, this is going to be the one time you're going to see it, and then you can sort of toss it out. Okay? But I do have to cover it. All right? This right here is the precise definition of a limit. Okay? This is the bona fide mathematician's way of writing out a limit, how to prove that a certain limit exists rather than visually, right? Or conceptually. This is the actual process for it, okay? So let me read it through really quick. and then I'll sort of show you guys the process behind it, okay? Let f of x be defined for all x not equal to a over an open interval containing a, okay? And let L be a real number, okay? Then we say that this is true, okay? If for every epsilon greater than 0, there exists a delta such that if the x minus a is less than delta, right, then the f of x minus L is less than epsilon. So basically what it's trying to say is that we can contain our outputs if we contain our inputs, essentially. Okay? So let me go through the process of how to actually solve this out using the precise limit definition. I'm going to do a simple one, okay? There is a QR code there so that you can verify, so you can look at what's actually happening behind the scenes, and I'll bring that up in a second, okay? So let's say I wanted to actually go ahead and prove that the limit as x approaches 4 of the square root of x is actually equal to 2, okay? So the way that this tends to work is this, that we start, let me put it over here, we start with this, right? And we work our way backwards, right? This is what I like to call the work. This is the sort of like the pre-setup of everything. The work is the backwards, right? But when we want to prove it, right, we start with this and go backwards. So this is sort of like the process that has to happen, right? This is actually the proof right here, okay? And it goes exactly how you think it goes. So we need to first do the work to get all of our values right, and then we go off and write it all up into a nice proof, okay? So let me show you guys what I mean, okay? We have to start with this tail end. We have to start with this first, okay? So what I'm going to do is I'm going to do the square root of x minus 2. We need to show that that is less than some epsilon. And we need to now, the point here is we are starting with this. We need to produce this somehow. And we need to get that delta so that we can sort of do the proof out, okay? In order for this to happen, right, negative epsilon. This is what this means. I don't need the absolute value here. Square root of x, there we go, x minus 2, okay, epsilon. So according to this, I can do plus 2 on both sides. So minus epsilon plus 2 has got to be less than the square root of x, which has got to be less than epsilon plus 2. Okay. I get to square both sides, so I can grab this entire thing, go squared. Okay. So that means minus epsilon plus 2 squared is less than x, which is less than epsilon plus 2 squared. Okay? And finally, what I can do at the very end is I can minus 4, minus 4, minus 4 on all of the inequalities. So I get left with this. Minus epsilon plus 2 squared minus 4 less than x less than epsilon plus 2 squared minus 4. Notice that the order got maintained, right? So now, this means what we get here, right, is the delta. Okay, it's the minimum of these two values. Minus epsilon plus 2 squared minus 4. Epsilon plus 2 squared minus 4. Okay, it has to be less than at least one of those two deltas. And we solved it out to get those two numbers in particular. Okay, Now, remember how I said, right? Downward, this is sort of like the work that we need, right? This was the work, the pre-work, the setup. We're essentially trying to find our epsilon and our delta, okay? This is the pre-work that needs to happen. The proof, right, is essentially this exact same thing, but backwards, okay? So now I'm going to actually write out the bona fide proof, okay? So let epsilon be bigger than 0, and let our delta value, right, be equal to this minimum that we found. Whoops, min. Come on. The minimum of the minus epsilon plus 2 squared minus 4 and epsilon plus 2 squared minus 4. Okay? If this is the case, right, then we have all the stuff backwards. Then that means let me get this right. Yeah. That epsilon minus epsilon plus 2 squared minus 4, okay, is less than x is less than epsilon. Epsilon plus 2 squared minus 4, right? And now we get to go backwards on everything. Okay? And we get, right, minus epsilon plus 2 squared is less than x, right, less than epsilon plus 2 squared. Take the square root, so minus epsilon plus 2 less than, I'm going to take the square root, that's what I didn't do. Square root, bam, bam, okay. Where are we going? Where are we going? So those two cancel, you get left with x, the square root. And I forgot to do the square root in the middle. Less than epsilon plus 2. And here we have minus epsilon less than square root of x minus 2. So I'm going to be minusing 2 on everything, right? Minus 2, minus 2, minus 2 is less than epsilon. And here we have our final statement, the square root of x minus 2 is less than epsilon. Okay? Like I said, unless you're studying math for the rest of your life, you will never see this again. I'm fairly confident, okay? If there's any questions, I think that's it actually, right? Yep, there's the lecture questions. If there's anything that, if questions come up on anything that I just covered, ask me during our quick check time. Stop by the math lab if you see me down there, come by my office hours, or just plainly send me an email, okay? Besides that, happy studying.